for
chemistry.
Yeah, baby. Yeah.
Sound. Yeah, I busted my glasses today, so if I'm squinting at the screen, it's because I can't see jack. Okay, all right. Hi guys. Yeah. So Born-Haber cycle is in AQA. Born-Haber cycle, I just seen someone put up, is it in AQA? It is in AQA. It's part of A2. It's one of the early things you'll learn at the start of year 13, maybe at the end of year 12 is the Born-Haber cycle. And it's linked, if you've done Hess's law, it's kind of linked to the same thing as Hess's law of energy cycles, enthalpy, and it's about the same thing that you can you can take an indirect route for a reaction or a process will be equal to the direct route, and that's essentially what that means. It doesn't matter which direction you can go through all the little steps. Now some reactions and processes are too hard to calculate through the direct route, so we have to use one of these cycles, the indirect route. Essentially that's what we're looking at today. Yeah, this is yeah, so this one is Haber cycle is a little bit difficult, but the only reason I'm going through Haber cycle is because I put up a little vote thing, and the Born-Haber cycle came up. Like most people said, oh, I wanna go through the Born-Haber cycle, so I thought, right, I'll go through that. Whereas most of the time, it's probably more useful for me to be doing AS stuff. Like I haven't done Hess's law yet or calorimetry. Which would have been better to do that in that order, but it doesn't matter. There's no point if I don't put the votes up. So we're going to go through the Born-Haber cycle. And so there is a whole bunch. Yeah. You did your A level into. I can't see what that says. Okay. Sorry, I have to look at my bald head sticking out there. Okay. So you got to know your definitions. Now, you haven't heard of this yet, unfortunately. Yeah, I know. But guess what? If you have a calculator, you can do it, and then you'll be ahead of the game when you come to this, all right? Sounds a little bit complicated then if you haven't done it from AS, but if you want to have a go, you can. If you don't worry, you can come back with a AS topic. So when I put the little voting system up, if you want to hit one of the AS, I'll generally put a couple of AS topics up and then maybe one A2 topic, and this time an A2 topic one out. So that's why we're going through Born-Haber cycle calculations. Now look at all these dirty, disgusting definitions that you guys have to know. So all these dirty, disgusting definitions. So does anybody know what an enthalpy change is? So an enthalpy change is the change in energy or the change in enthalpy during a reaction, or change in heat in a reaction under constant pressure. Yeah, that's right. The energy released during a reaction, or the energy change, because overall the energy might be endothermic, so it might absorb energy. So it's the enthalpy change during a reaction under constant pressure, okay, or the change in heat in a reaction. Oh yeah, you're on A2, so this is cool. You'll be able to do this. This is kind of like, if you've done, that means you've done Hess's law, energetics, you've done calorimetry, and you've done bond enthalpies, so you'll be all right with this. So you've got these horrible definitions, and this is just gathering some of those together. Some of them you'll already know. Constant pressure, that's right, standard conditions, yeah. So you've got to know what the enthalpy of formation is. You did that. You should have done that in AS when you did Hess's law. So does anyone know what the enthalpy of formation is? We're going to go into the big dirty calculations, but I just want to go through the definitions. Okay, someone's got it. Well done. Enthalpy of formation is the energy released when 1 mole of a substance is formed from its elements in their standard states. Very good. Nice definition. Yeah, that's right. Standard states is really important with the enthalpy of formation. So, yeah, it's direct. You're just going from the elements in their standard states and forming a compound. Now, enthalpy of atomization, there's two in here that are a little bit tricky, where there's a little bit of a nuance to them, and that's the enthalpy of atomization and electron affinity, which we'll come to. Now, the enthalpy of atomization is, what do you think? It's when you form 1 mole. Yeah, forming bonds is exothermic. Yeah, breaking bonds is endothermic. That's absolutely right. And the overall energy change is the calculation between that, i.e., if there's more energy released from bond making than is absorbed in bond breaking, then the overall reaction will be exothermic. And if there's more energy absorbed in bond breaking than in bond making, then the overall reaction is endothermic. Most reactions, 90% of the reactions that happen naturally in the world, just under the conditions on the Earth, are going to be exothermic, because things are trying to get to a lower, more stable energy level. And when you form products that are more stable, you release that extra energy you had to the environment. So most reactions are exothermic by nature. Oh, nice one, important 45. The enthalpy change when 1 mole of gaseous atoms is formed from an element in its... yeah, so when the key here is when 1 mole of gaseous atoms is formed. Now, there's a key here with the enthalpy change of atomization you need to be careful with. If you're dealing with a diatomic molecule like oxygen, you've got to remember the enthalpy of atomization would be half. If you take an oxygen molecule O2 and you break it down into 2 O gaseous, into 2 gaseous atoms, you split 1 mole of oxygen molecules, you're going to get 2 moles of gaseous atoms. So that's double the enthalpy of atomization. The enthalpy of atomization would be half a mole of oxygen molecules. When you break half a mole of oxygen molecules down, because it's O2, you'll get a whole mole of oxygen atoms, and that's the enthalpy of atomization. So you've got to watch out for that one when you're dealing with diatomic molecules. Bond dissociation enthalpy. What do you think of when you hear the word dissociate? So this is kind of easy. It's when you're breaking bonds. So the enthalpy change when 1 mole of a specific bond is broken, right? Yeah, it's split apart. You've got first ionization energy. You'll notice from AS, the definition of the first ionization energy, God knows what it is. It's 1 mole of what? What is it? When you remove 1 mole of electrons, what is it? First ionization energy. You remove 1 mole of electrons. God, I've forgotten the definition. It's under gaseous conditions, isn't it? Does anyone know? You should know if you're doing AS. My brain's too dumb to actually remember what it is. The minimum energy required to form 1 mole of positive gaseous atoms be ions, wouldn't it? So enthalpy change when 1 mole of electrons is formed from 1 mole of solid ionic compounds to form 1 mole of -1 ions. 1 mole of electrons removed to form 1 mole of positive gaseous ions. Yeah. Okay. And you've got to vaporize it first, haven't you? So it's 1 mole of gaseous atoms. So it's when 1 mole of gaseous atoms become 1 mole of +1 positive ions, right? The energy change. And then you've got the second ionization energy is when you take 1 mole of gaseous +1 atoms. No, 1 mole of gaseous +1 ions. And you convert that to 1 mole of gaseous +2 ions, removing another mole of electrons. Gosh, that's disgusting, isn't it? And then we've got some other ones here. We've got the first electron affinity. So this is when you gain electrons. So it's going to be when 1 mole, again, you've got to be in the gaseous state. So when 1 mole of gaseous atoms gain electrons to become 1 mole of gaseous -1 ions. The second electron affinity is going to be, if you're asked for a definition of that, it's going to be when 1 mole of gaseous -1 ions become 1 mole of gaseous -2 ions. Okay, they gain electrons to become 1 mole of gaseous -2 ions. So it's always in the gaseous state, these ionization and affinity, from the start and to the end. So they go from atoms to ions in both cases. Of course, electron affinity is going to negative ions. You're gaining electrons. Ionization is losing ions, so you become positive. And you don't have to be a metal or non-metal. a metal, you can do it with either, basically. I know we're used to metals losing electrons, but we could be looking at the first ionization energy of oxygen and affinity of a metal. It doesn't really matter. Okay, anyway, enough of that waffle. The last couple to waffle on about is the enthalpy change of solution. Okay, we've got something called the enthalpy change of solution. So that is when you take 1 mole of like an ionic lattice, and you form 1 mole of aqueous ions from 1 mole of a lattice under standard conditions. Can you tell which group an atom is in from successive ionization energies on a table? Absolutely, of course you can. Yeah, you can. Yeah. Wherever you get a big jump, that tells you you're breaking into a new energy level. Small jumps, you might be going from 2p to 2s. So if you've taken electrons out of the 2p orbitals, and you might get a little jump in between subshells. They're called subshells, like you've got 2s and then you've got 2p. But when you go from the whole quantum level of 2 and you're breaking into the next energy level, there will always be a massive jump, and that's how you tell what group it's in. So yeah, if you can tell magnesium is in group 2, how can we tell magnesium's in group 2? Because the third ionization energy will have a big jump. First 2 electrons, easy to remove, it's group 2. But when you try to remove the third electron, that's coming from another energy level. So you're breaking into a new energy level. What's that? 1s2, 2s2, what's magnesium? 2p6, 3s2. So you're removing the 2 3s electrons for magnesium, and then you're breaking into 2p6. You're going into another energy level. So you're looking at a jump on the third ionization energy. If you're looking at group 5, if you want to know if an element's a group 5 element, you'll get a big jump in the 6th ionization energy, because you remove the first 5 from the outer shell. If you think of old GCSE style with the rings, and then you're breaking into the next ring, you're going to get a big jump on the 6th. So that's how you can tell the groups. So the big jump happens when you break into the next ring or the next quantum energy level. Okay. Enthalpy of solutions. Yeah. Oh, let's have a look. I've got the definition somewhere. I do actually have the definition somewhere. Where's my definitions? I've got the definitions here. What is the definition? Enthalpy of solution is the enthalpy change when 1 mole of a solute is dissolved in enough solvent so that you get no further enthalpy change. That's quite a disgusting definition, but it's the energy change when 1 mole of a solute, so something like sodium chloride, magnesium chloride, salts basically, is dissolved in enough solvent that you get no further energy change. And yeah, and then what was the other one we had? We had another one there. What was we got the enthalpy change, lattice enthalpy of formation. This is the enthalpy change when 1 mole of a solid ionic compound is formed from gaseous ions under standard conditions. So let's have a little look. Where am I? I'm over here. Okay, let's go on and do some questions. Yeah, it's a lot to remember, but we're going to go through the calculations. I mean, this won the poll, so I thought there might be some A2 students who wanted to go over this. Yeah, if you're doing AS or you haven't done this yet, it can be a little bit difficult. So here we go. Which equation represents the process that occurs when the standard enthalpy of atomization of iodine is measured? So we got 3 here. Is it half I2 solid goes to Ig? Is it I2 solid goes to 2I? Is it half I2G goes to Ig? Is it I2G goes to 2Ig? What do we reckon? Oh, well, Brass Boy, you should be able to get this. The first, the atomization energy of iodine. So everyone's having a little bus at D. And if we were doing electron affinity or ionization, you need gaseous on both sides. But the very word atomization means you're going to gaseous atoms. So this is actually when an element under its standard conditions is turned into gaseous atoms. the energy change when 1 mole of gaseous atoms is formed from its element, and it's got to be 1 mole of gaseous atoms. So what would you go with now that I've told you the definition? When 1 mole of gaseous atoms is formed from its elements under standard or its elements in standard states, yeah, it's going to be A. And the reason is, I know iodine, there's no such thing as Ig, right? As in, when I say there's no such thing, iodine doesn't exist naturally like that. Iodine exists as I2, and it's a solid. So what you've got to watch out for atomization, you're going to need half of the diatomic molecule to make 1 mole of atoms. So just watch out for that in equations and stuff. That's the equation that accompanies atomization. Okay, now this is a bit random because I just popped this up here without you guys probably having a clue. So draw a line from each substance to the enthalpy of lattice formation of that substance. So how would you possibly know that? Do you have to know these off by heart? No, you don't. What you do have to know is these are all ionic substances, and they form lattices, giant ionic lattice, right? Essentially, the enthalpy of lattice formation is the energy released when we form the lattice. So to just give you an example, like if you have Mg2 plus, oh my days, this is going to be disgusting. I should have probably thought about this before doing it. We're going to go on to the dirty Born-Haber cycle questions in a minute, which are actually pretty easy. So if I put these bad boys together, and the enthalpy of lattice formation, by the way, is in their gaseous state. That's a bit crusty. How do I show they're a gas? I've got no idea how to show these are a gas, so I'm going to put G next to them. They're ions in the gaseous state, and then they're going to come together, right, to form... Oh, that's just long. Where's the little delete button? There it is. Let's just do that. Plus 2. You remember this from GCSE. Ionic compounds, the structures. You go like this. Oh, my days. That is ugly. Yeah, so you got the idea. I'm going from gaseous ions to that. Now, what would you say is more stable for these atoms to exist as gaseous ions or to get together in an ionic lattice? What do you think is more stable? You're absolutely right, Gertie. The more exothermic, the stronger, the higher the lattice formation enthalpy, because it's releasing energy, saying I'm at a much more comfortable place now, get rid of all this energy. So yes, the lattice is going to be more stable than being a gaseous ion. So for all of these, you're going to have really exothermic lattice enthalpies of formation. We know that sodium and chlorine like to exist as sodium chloride in a giant ionic lattice. So if you have gaseous sodium ions, gaseous chlorine ions, they're going to come together and form a lattice. And when they do so, they're at a lower energy level. They're going to release some of that energy they had. And so it's going to be exothermic. So the more stable this ionic substance is when it forms its lattice, the more exothermic it's going to be. Which one do you think is more stable? Magnesium chloride, magnesium oxide, barium chloride. And then when you know that one, you can draw a line to the one with the most exothermic. What do we reckon, guys? So important 45, you are spot on. It is going to be this one. Why? Because that's 2 minus and 2 plus. So stronger ionic bonds, right? Stronger electrostatic forces of attraction between the oppositely charged ions. But then we come down to, is barium 2 plus? Oh, I can't really remember. Magnesium and barium are both 2 plus. Ooh, now we got, who's going to be more stable? Magnesium chloride or barium chloride? Which one is going to be more stable? Both are 2 plus and 1 minus for the chlorides. So this bad boy is 2 plus. Now we've got to think about size and what we call charge density. So the ions are going to be more stable if that positive charge is spread over a smaller space. So then it's got a higher charge density. So what's smaller, magnesium or barium? Magnesium's the smaller ion. Good. So magnesium goes next, is the next most stable lattice. Because magnesium is smaller, and you can look, it's higher up the group in group 2, and barium's right down near the bottom. So barium's 2 plus charge is spread out over a bigger ion, so it is less stable than this bad boy. It's still pretty damn stable. It still prefers to be barium chloride, right, rather than gaseous barium and chloride ions. They still atoms or ions. Yeah, they still prefer to be together like that. Okay. So our whole, yeah, the bigger the, yes, kind of, the bigger the positive ion, the less charge density it has. We'll come on to polarization a little bit later when we get on to looking a bit at that. I probably need to get on and do a Born-Haber cycle. So guys, this here is a Born-Haber cycle. Woo! Yeah, lovely. It's a Born-Haber cycle. What the hell? Haber, I guess there was a guy called Born, like, I don't, you ever seen, I don't know if you've ever seen the Jason Bourne movies. Has anyone ever seen the Jason Bourne movies? You might have done.
Stick around.
I'm gonna have to science the shit out of this.
Well, yeah, that was Matt Damon who plays Jason Bourne. No, he didn't come up with this, but a guy called Bourne did. And I'm guessing, well, I don't know, maybe Fritz Haber had something to do with it. Could he have had something to do with it? I doubt it. Although I don't really know any of the origins of the name, so I'm just going to shut up about the Haber process. Yeah, it might not have anything to do with it. I don't know whether it was the same Haber that gave his name to this, but this is known as a Born-Haber cycle. So let's get into it anyway. What the hell is this all about? We see this here. This is in green. This is the enthalpy formation of sodium chloride. Now this is what you learn in AS about formation of a compound, sodium chloride. There's the compound NaClS from its elements in their standard states. So there we go, sodium solid, chlorine gas, and we want to calculate that energy. Now this is like a Hess's law cycle. So what we're saying is, if we know all of these, they're going to, all of these other steps are going to be equal to that. So minus 411 is equal to all of this, right? So because we know that's minus 411, we can work out any missing part of this from the cycle. And you can do that by saying minus 411 is equal to all the other numbers plus x, which is our unknown, and then you just rearrange to find it. That's one of the ways. I'm going to show you the two ways to do it. So if anyone has their calculator, how we want to set this out is like this. This here is how you write the atomization of chlorine. So you see chlorine here is in its gaseous state, but look, chlorine is diatomic, but look here, it's become an atom. There's no diatomic symbol after it. So it took plus 122 kilojoules, so that means endothermic energy in to turn chlorine gas into chlorine atoms. Our sodium we've done nothing with yet. We're then going to atomize sodium. We're going to turn sodium from being solid to a gas, and that takes 107 kilojoules per mole, and now we've got sodium atomized into gaseous atoms. We then want to turn sodium into an ion, and we can do that by taking a mole of electrons from it, and that's how much energy it takes. We then want to add those electrons to chlorine to make chlorine ions, and that is the first electron affinity of chlorine. And now we have this. This is easy to get confused with this. This is the formation, same thing, sodium chloride giant ionic lattice, but like that diagram I showed you before, from its gaseous ions. So this is going to be very exothermic, hence the big arrow, because we're going to go from unstable gaseous ions to a solid lattice. And we're asked, how do we work this out, guys? How do I calculate what the lattice enthalpy would be? So is this order always the same? Order, it's similar. Sometimes they will swap around atomization, but you'll be able to work it out from these equations. So you know you're looking at atomization when you're going from solid to gas. You know that's not ionization. And then you'd know you are right. Occasionally they flip. They do like, they ionize. They normally atomize, then ionize. But I have seen ones where it's a little bit twisted before on the way up here on the left hand side. Electron affinities are always here on the right hand side, and the lattice enthalpy of formation is always here. You're not always asked to work out that. Sometimes you'll be asked to work out this. We're going to do some examples. So for this one, you're going to go, I'll show you how to set this out then, folks. So you should be able to work this out. Let's see if you can rearrange this. I'll give you the working. There you go. This is one way to do it. I'm going to show you both ways, and then you pick which way out the two ways you prefer. Because I used to use one way, I now use this way. So I just write minus 411, and then I'm going to put equals 122, 107 plus 496. I'm going to come round here and write minus 349 plus x. This is my x. I put a question mark. Should have really put an x. Like algebra, bit of algebra, right? And now we're going to solve. So who can solve that? Yes, this is AQA Invalido username, but this is also OCR and EdXL. Anyone who does Born-Haber cycle, they're the same for everyone. For all chemists everywhere in the world, and whether you do a chemistry degree, you will have to do Born-Haber cycle. It's given us this diagram. It's given, you will get this diagram, or you will get a diagram where some of these are blank and you've got to write the equations in. We're going to look at some of those as well. So we're going to do like 3 or 4 examples. Nice, liking it. You're close there, Galathus. I think there's just a slight, yeah, important 45. I think you got it right. H6 equals H2 plus H3 plus H4 plus... might be. No. Important 45. I think you got it right. Yeah, it's minus 787. Minus 787. So all you're going to do here, I'm going to put the working out. Like normally I type this all in, but you know, oh, I've just mashed my tongue up. There you go. So that's your working, how you can do it. Look. You're going to go minus 411. You add all these numbers up and you should get 376 plus x minus 376 from each side. And if you go minus 411 minus 376, we're going to get minus 787 equals x. Now, for those of you that are absolute poop at rearranging, I'm going to show you the other method. Although if you like, I like just doing it like this, then you do it like this. But I'm going to show you the other method. All right. The other method is, you might have done this with Hess's law. If you did Hess's law, where you got to draw the big dirty arrow going around. So let's have a look at that method. My eyes are so brock. Right. Where am I? Here I am. Okay, so this is the other method, guys. This is the other method. Some of you might make a mistake on one of them. I've got about 3 or 4 of these we're going to go through, because these are the big fat markers that are going to come up. I know we looked at definitions and stuff. Those are like multiple choice, 1 mark, 2 mark. But these are the big ones that could be like 4 or 5 marks. Okay, and they're so if you don't know how to rearrange all of this, what you can do is, like with Hess's law, you can draw an arrow going, oh my gosh, it's doing that thing where it makes everything go straight. You draw the arrow like that, and you basically start from whichever bit is missing, and you draw anti-clockwise like this with arrows, and then all you do is you put these in, and what you're going to do, this is a bit long this way actually, but this is, some people like this way. I mean, it's a bit long, but what you do is you go like, if the arrow's in a clash, you see this arrowhead is clashing with this arrowhead, then what you're going to do is put a minus in front. So you're going to go minus, and then brackets, minus 349, and then because the arrow is in a clash here, we're going to go minus plus 496 in brackets, and they're all clashing all the way down, minus 107, minus 122 in brackets, and then because the arrowhead is in alignment here, you go plus minus 411 in brackets. And if you smash that in the calc, you should get the same answer. You can double check that I'm right on that, but that's just to give you two methods, because some people yeah, prefer doing this method. So this way you go minus, you always, sometimes when I do this method I forget on the first one to put the minus in front where it clashes. So you go minus 349, minus 496, minus 107, minus 122, plus, and this one is always plus because your arrow when you go backwards is always, you always put a plus on that, and then you go plus minus 411 and you get the same answer. So it totally depends which method you prefer. So you can, this is the big fat Hess's law kind of arrow method, or you can do the other one. All right, let me test you on another one. Okay, what we got to do here, peeps? I don't even know what we got to do. Oh, here's what we got to do. So look, they've given us all the numbers. We've got all the numbers. We've got to find, this is X this time. We're going to have to find so the question would be 3 marks, use all the data. Often this data will not be written nicely. I'll show you an exam paper one. These are CGP ones, but I'm going to show you an exam paper one in a second. Most of the time the data is in a separate table, and then you have this and you've got to work out what's what. But could be 3-4 marks, so, or more. Especially if you've got to write some of these equations in. We'll look at one of those. So see if you can work out X. You can either do the rearranging just method, and if you're doing the rearranging method, just go minus 548 equals all of this plus, so all of this plus X, simplify by adding all those numbers together, and then rearrange to find X. Or you can do the arrow method. If you do the arrow method, all you're going to do is start. This is a bit weird now because it's this one. So we've got to go anti-clockwise, and you're going to want to start from there. Oh my good gosh. We're going to want to start here. So if you're an arrow person, you're going to start here. This is terrible. And you're going to go all the way round to there. So what you do if you're an arrow person, just draw the arrows on. Where you see, this is always in the right direction. So I'm going to start here and go minus plus 249 plus minus 548, and then minus 3791, because these are all going to be in clash. So it's totally up to you what you do. Let's see what you get. 148, 145, that sounds pretty good. The water purple arrows show what has to be done to magnesium and oxygen until the formation. Yeah, you're right. Yeah. So, no, well, you can go directly from magnesium. So the green arrow is basically you can go directly from solid magnesium atoms and oxygen gas, obviously, and just react them to make magnesium oxide, right? It can be quite difficult to measure that experimentally. So what you can do is you can use this calculation to calculate something that would be too difficult to measure experimentally. So you can do all of this, and once you know all of these individual steps, you can work out any one of the steps in between. But yeah, 705 Brass Boy. I think 148 is sounding more like. Okay, so let's have a little look. This is the rearranging method. So if you're wondering, let me show you the rearranging method. That's what you want to do. So you want to write minus 548 plus, and then minus 548. The green is equal to all of the purple. So you're just going to go equals that, add those all up and simplify. So when you calculate it, just go 249, skip the X, plus 738, plus 1451, plus 798, minus 3791. You don't need to change any of the signs when you do this method. And then you're going to simplify, and you're going to get that. Minus 548 equals minus 696 plus X, add minus 696 to each side, and woo, you get that. The big arrow, Right, important 45. The big arrow always goes anti-clockwise from the missing element and work back round to the missing piece of the puzzle. If you're doing the arrow method, let me show you the arrow method. Here's the arrow method. A start here, right? You start here, and I'm going to put it up for you. So if you want to use the arrow method, this is the arrow method. You're going to get to 148 again. So we're going to go, we're missing atomization. So I start there, I draw the big arrow anti-clockwise round until I get back to there. And then I follow the numbers and I go, right, they're not in accordance. So I'm going minus plus 249 like that. And this is the only one that's ever plus. I'm going to go plus minus 548 minus 3791 and then minus 798 minus 141 and then minus 1451 in brackets and then minus 738 in brackets. The brackets are really important with this method. If you start changing the symbols in the brackets, you're going to screw up. You only change the symbols outside the brackets. And really, the plus is only ever this one. Everything else is always minus on that method. So that's that method. So it all depends which method you prefer. Let's have a go at an exam question on it. Let's do like an AQA or OCR. Some of these are OCR, some are AQA. Let's have a look at this one. Let me just see if my yeah, I better shrink my fat head down. I can't see that, man. My eyesight is so bad. I'm like a mole. Right, the figure below shows an incomplete Born-Haber. That's what I'm saying. Is it Jason Bourne from the movies and Fritz Haber of the old 3H2 plus N2 goes to 2 molecules of ammonia dude? Or is it somebody else? Yeah, anyhow. Born-Haber cycle for the formation, because if it's Mr. Haber, he did a lot of stuff. Born-Haber for the formation of calcium chloride. So what are we being asked? It says complete the figure by writing the formula, including state symbols of the appropriate species on the 3 blank lines. So we've got 3 blank lines. Calcium chloride S, that is the enthalpy of formation, always is. This is always this. So you can work that out. What do you think goes here, folks? Because that's always the enthalpy of formation. So, yes. Well done, Gertie. Because it... what happened? Oh, my gosh. I now got to check. I don't know. I hit the mouse pad. It all went a bit Pete Tong there. I started hitting the mouse pad all a bit weird. Ugh. Okay. I need to get more sensitive. I need to become more sensitive. Yeah, so this is going to be from elements in their standard states. So calcium solid plus chlorine in its standard state is going to be Cl2 with a G. Okay, just chlorine gas. So Gertie, you got it absolutely. This arrow always points down, this one. This is the down pointer, because this is the enthalpy of formation for this one. That arrow there, I don't know why I drew an arrow there. There was no need for me to draw an arrow there. That was me just saying, hey, fill in the blank. What about this one, guys? What should go up here? I like the fact you guys have already calculated the value. What is it? Minus 795. Methinks you're wrong, guys. There's a little mistake in your calculation. You're on the right way. You're on the right method. You're slightly wrong. But you're in the right ballpark. I don't know if it's a calculator error, but you're close. You're close to the first part of the question. This is a 5 marker, I think. So we've got to get all 3 of these right first. Well, let's have a look. It looks like what has changed between this level and this level. The chlorine is still a molecule and still a gas. The calcium has been atomized. So this was the first atomization energy of calcium. Then it looks like the chlorine is still a gas. Calcium has been ionized. I'm going to go for it's the second ionization energy of calcium, right? We're going to go second ionization. But I get what you're saying. Is it do they now ionize the chlorine? Do they now atomize the chlorine and then ionize the calcium there? I think because they've done the first ionization, we're going to have second ionization. So I think this should be Ca2 plus, and that should be our change. And now we're going to be like that. And then Cl2 still gaseous. And then this is going to be up here that we're changing that to that there. So, and actually we can see because, yeah, we can go in order. They've probably got the order. Enthalpy minus 795 is over there. Enthalpy of atomization of calcium plus 193. First ionization energy of calcium 590. They're telling us the order. Look, second ionization energy of calcium. So this was the second ionization energy. And then over here is going to be the enthalpy of atomization of chlorine is there. And then the electron affinity of chlorine is here. So we're going to want to go to... Ooh, this is a brute. Yeah, this one's quite hard, writing this one out. So we're going to want Cl minus over here, from here. And we just want to write the electron affinity. So I'm going to go Ca2 plus 2E minus plus 2Cl minus. Sorry, I didn't put the gaseous states in. All right, let's put them in. Right? Now, when you're doing your calculation, did you remember when I talked about atomization, ionization? What have we got here? The first electron affinity over here of chlorine is minus 364. That's for one chlorine, but we've got two chlorine. So we're going to have to double this in our calculation. And you're going to need to, yeah, so you need to double that. Yeah. I'm doing everything. Like I'm doing all of the topics. I'm just working through with a little vote every week on what do you want me to cover. So some of them are AS, some are A2. So this is the first A2, I think. Most of them have been AS so far. So I just put it up and then people vote on what they want to do. I'm imagining as we get closer, people are going to want more A2. Let me put in... There you go, guys. That's the answers for this first bit, not for the calculation. Remember, your definitions are for 1 mole. Where you have more than one, you need to multiply. So I'm just kind of give you a cheat code there that is going to be double bubble. Now you can do the arrow method. You can do the reverse arrow method, or you can do the you can do the enthalpy of formation is equal to. Oh, yeah. We don't need the 2E minus. Yeah, the 2E minus is wrong because the 2 electrons here, that was me just being an idiot. The 2 electrons here are onto the chlorine. So I can't have plus 2E minus as well. Otherwise the charges won't balance. Well spotted. You know what? I'm a little bit of an idiot. So, what can I say, guys? Sometimes I'm a bit of a bozo.
Whenever I'm about to do something, I think, would an idiot do that? And if they would, I do not do that thing.
Yeah, so I've got to check myself sometimes. Yeah, you're right. It shouldn't be 2E minus. Okay. Right. Now let's check out this calculation that you guys have been doing. So... what method you guys doing? Yeah, I know. It's not 469. It's not. Okay, let's go through it. Let's bust out the calculators. Let's go through it. Which method should we do? Let's try the reverse arrow method. Let's say we're doing the reverse arrow method. What are we actually calculating? A value for the... Ooh, okay, there's a little trick here as well, which I'm going to get. So, you see this arrow? This is different to how we normally have it. This arrow is going up. We can't calculate. What they've asked us to calculate is impossible to calculate using the Born-Haber cycle. They've asked us to calculate the lattice oh my god, that's ugly. They've asked us to calculate the lattice dissociation of calcium chloride. You can't do that with the Born-Haber cycle. You can only calculate the lattice formation, but they're equal but reverse symbol. So I'm going to calculate lattice enthalpy. Oh my days, what's going on there? Of formation. So we can calculate this, right, from the Born-Haber cycle, the lattice enthalpy of formation. And if I want to know dissociation, oh my god, can I get rid of that? That blue thing has upset me. There. If I want to calculate this, the lattice dissociation of calcium chloride, I just have to reverse that symbol at the end. But let's calculate the lattice enthalpy of formation first. So you can try this method, yeah? Go with this. Draw your little arrow going in the opposite directione. Write your numbers in. So this is the electron affinity. So they're in order for us. So I'm going to go minus 364 times 2. What is that? That is the enthalpy of atomization of chlorine. So that was that bit. So that's plus 121. These are all going against the arrow. So I want, if you want to do the arrow method, you're going to start with minus 364 times 2 in brackets. That will be your starting point. And then what we're going to do, we're going to go, what's next? Minus, I'm kind of losing the, this is looking so ugly here. Minus 1150, then minus, I might have put these all in the wrong order. I'm not really looking too much. I'm just whacking them down. And then minus 193. And now this one, the arrows are in sync. So we're going to go plus. And what is the enthalpy of formation of calcium chloride? 795 minus 795, sorry, in brackets. Smash that all in your calculator. Tell me what you got, people. Let's go. We'll do the rearrange after. So I'm going to go. All right. Why don't I just type that out for you? Let me type that out for you over here. So if you want the big arrow method, put this in your calculator. Minus 364 times 2. Hey, is there anything else I got to times by 2? What did we... Oh! We got to times the atomization of chlorine by 2. Yeah, that's why we're making mistakes here, peeps. Although I haven't done it yet, but I just spotted it. How do I do that? Right, so I need that times 2 as well. You might say, why have I got to do atomization? The atomization of chlorine is the formation of 1 mole of gaseous chlorine atoms. And that would be from half a mole, but we got a full fat mole of chlorine molecules. So we've made 2 moles of chlorine atoms. So we're going to double that number as well. So, anywho, let me put it all in. No, did he? Right. Minus 364 times 2. Minus 121 times 2. And then I want to go minus 1150. This is where you only have to put the wrong minus in a bracket or something and you're screwed. 590. What we got, peeps? Minus, some of you have probably worked this out. By the time my brain's worked it out, you should be there. Oh, the last one is plus because it's the formation, but then it's minus 795. Right, what does that give us, guys? Anyone got an answer? Woo! Nice. You are getting minus 22. Lovely. You've got it. Minus 2242. Spot on. Don't put the 0 in front. Now, that's going to get you 3 marks. We need to flip the sign. It's impossible to calculate, put these numbers in and get the positive sign out of plus 2242 as far as I'm concerned, because the Born-Haber cycle can be used to calculate any of these, and that's the lattice enthalpy of formation. The exact reverse is the energy to go from a lattice to gaseous ions. And you just ask yourself, would it be exo or endothermic? So you want to take a salt and we want to reverse it from calcium chloride. We want to turn them into gaseous ions. They ain't happy about that. They're going to be in a higher energy state, more uncomfortable, more energetic. You're going to pile in energy. So it's the final answer is going to be plus 2242. So just check, like, you are taking these guys to a higher energy state by adding, overall, there is energy added in to go from a nice salt crystal into these gaseous ions. Okay. Yeah, so it's endothermic the other way, whereas the lattice enthalpy of formation is always going to be exothermic. So the arrow would be going down. I drew that big blue arrow going down. That's for the lattice enthalpy of formation. So calculate that first, then check the answer. Did they want formation or dissociation? If they wanted dissociation, flip the sign. The minus is in between the brackets. That's just the rule when you're doing the arrow. We could have done this the other way, guys. We could have written this. Okay, so here's the other way. Some of you don't like this way. Okay. Oh, I would have saved myself a lot of time. I didn't realize I had that already written there. All right. So the other way, you can smash this in the calculator and then see what you get with this way, okay? Minus 795 is equal to 193 plus. So you can see which way is easier. I don't know if I... 1150 plus, I suppose that's hard, the older that you've got to times that by 2. That should be in brackets, but I'm lazy. And then, oops, minus 364 times 2 should really bracket that because I'm lazy. And then, oh, plus x for the lattice enthalpy. And then, yeah, I won't bother solving it, but you should get the same thing. If you do all of that, you know, whatever number that is on the right-hand side, subtract or add that, whatever you've got to do, depending if it's a negative. Is that going to be a negative number? No, no. So it's going to be a positive. It's what's that? 1447 minus 795. I think it is. No. Yeah, whatever it is. So you can do that. I will put up the blank question again. Have I got a blank? I've written all over it. Yeah, I can. Do you want the one with the invalido username? Do you want the blank one with the equations filled in, or the total blank original? Let me put that up there. Oh, geez, Louise, where are we? Total blank. I'm gonna blank this out for you, dude. We're gonna go. No. Now, oh my days. There you go. That is your blank. Yeah, I think you typed something in wrong there. So, but it could be me. I could have just typed something in wrong on my working out. It happens when you go in like that. Especially when you're going live, you're always going to make mistakes, and then, like, you know, afterwards go, what the hell did I should have done it like before. I think I might have done it before. Did I do it before and after? I don't know if I did. No, that's an arrow. No, I don't want any of that. Okay. So you should get minus 2. What was it? 2242? I can't remember what we worked it out as in the calc, because I let you guys work it out. $2242. Did that get 2242? Let me just quickly check that. So 193. Have I missed anything out there, guys? 590 plus 1150 plus 242 plus, oh my god, no, not plus. I need to minus 364 minus 364. I got one. Okay, so I worked that out like this. Minus 795 is equal to 1447 plus x. And then what I'm going to do is I'm going to take 1447 from each side. So we're going to go minus 795 minus 1447 equal. Oh gosh, no, I've done that wrong. Hold on, what have I done? Done something wrong there. Oh, yes. Thank you. I don't know why I'm going to put that in my calculator. It mashed me in the head. So then I'm going to get like x is equal to minus 2, 2, 4, 2. Yeah, good. So you could do it either way you prefer, guys. You could do it either way you like. You can do it the arrow method or that method. What I should do... oh my days. What's that? What's that? Okay. What does that mean? Ah, right. Hold on, guys. Uh, I don't know what to call this. I don't even know if it's a proper one, but yeah, let's just do that. I don't know which way is the better way to do it. So what do you reckon? I put up a little poll. Have a quick vote. What's the best way to do it? Is it the what method is best? Hey, Galatheus. Minus 2242 is the correct answer, Gala. But what it is you reverse the sign. You can't get, you're always going to get that minus 2242, and then you just reverse the sign for the correct answer. So the reason is because what you're actually calculating with this is you're calculating this, because I'm blubbering away here, but you're calculating this. No matter which way you do it, you're calculating the arrow down. And then because the question has asked for dissociation is going up, you just reverse the sign. And so you just have to know that. That's just something you've got to know. A little bit like when you do calorimetry. Have you done calorimetry in AS? And you get your answer and you're like, is it plus or minus? Calorimetry, you're burning something, combustion, so it's always exothermic. You have to put the minus in. This is the opposite when they ask you for dissociation. Okay, cool. All right. Let's get on. Oh, I tried to do a little poll. I don't think it worked. Tried to bust out a little poll. 71% said yes. Okay, yeah, cool. There we go. Just trying to get used to the stuff. Right, let's bust out another question. All right, one more of these, because then these get a little bit long. And then what I'm going to do, what's the time? Got time? Yeah. I think I might do a little bit of, there's another equation, enthalpy, a solution. But you're going to be taught this at school, and you're going to, if you haven't been taught this already because you're in AS and you haven't done this, you're going to have a head start, because some students are going to find this really hard and you're going to look like serious dude or girl or dudette, because you're going to be able to do this in class. And if you're here revising it for A2, there you go, good practice. It's always good when you're going to revise a topic, hammer it with like 5 or 6 questions, because yeah, you want to get that drilled in. And then what you do, once you've got it and you're like, yeah, I've got it, what you need to do is set on your mobile phone, on your smartphone, set a reminder for 4 weeks time or 3 weeks time, where you're going to do one more practice. You're going to go, oh yeah, I've got to do a Born-Haber practice. So what you do is you crack it now and you're like, yeah, I've got the hang of it. And then you say to yourself, set a reminder. You go on physics and maths tutor, you go to thermodynamics, you find a Born-Haber cycle and you have a go at one. And you can, if you're AQA, you can go on the OCR content and have a go at Born-Haber cycles. They're going to be the same. And if you're OCR, you can go to the Born-Haber cycles for AQA if you want to do one that you haven't seen before, because sometimes you do them all and then there's no more fresh ones to do to test you. So do that. But so when you've revised the topic, just set a reminder and come back to it in like 3 or 4 weeks for A-level and test yourself on it. If you've got it, if you've smashed it again, no problems, then you set a reminder for 2 months and you say, right, I'll check that back in January, Born-Haber cycles. I'll put it on my phone, set a reminder, revise, do a Born-Haber question. So You wait a month, see if you get it right, then give it 2 months. And that's how you can go with your topics. And if you make a mistake, then it's like, okay, I need to go back to it again. In like, if you make a mistake in a month, you say, okay, let me do a 2-week reminder. I'll have another go in 2 weeks, see if I've got it. Anyway, yeah, that's a special German, that's a technique they do in Germany. I can't even remember what it's called. I think it was devised in Germany. I might be making that up. It's a way that they revise, like to keep your long-term memory. So when you crack something, like if you're doing biology and you've got all your respiration equations, you're like, I've cracked it, I've got it. You go, okay, let me test myself in 4 weeks. If I've still got it, then I'll extend it to 2 months. If I've still got it in 2 months, then I'll extend it for 3 months. So till I look at it again and like that. Right. What have we actually got to do here? I'm guessing they're saying calculate the electron affinity. And they normally kind of go in order in the table here. So where's the electron affinity? This is going to be the electron affinity right here. It's always this down bit here. So this is our electron affinity. Have a look, folks. It's got the old double bubble. So when we get our answer, we might have to approach it differently. See if you can do this. So if you want to do the arrow method, you find the bit you're missing and you go anti-clockwise around. So you're going to start here to go anti-clockwise. And you're going to come all the way back round if you like the arrow method. And then you're just going to smash these in. I'm not too sure about the arrow method on this one, but I think it'll all work out for the best. Let's see. Or if you don't want to do the arrow method, you find the enthalpy of formation. That's here, -828. And you do this method. You go, right, that's -8. You kind of got to write these in, I guess. First ionization energy of strontium. Oh, God, it's a pain to write all these in. Oh, these aren't in the right order. What a bummer. So that's the first ionization energy of strontium. Okay. Oh, yeah, that's the first ionization energy of strontium. Second ionization energy of strontium. So what's that? That's 1060. That's 548. I don't know if I got... It doesn't even really matter if I screw this up because atomization of chlorine. Oh, is it the dreaded double chlorine? Yeah, look. Molecule of chlorine going to 2 atoms of chlorine, 2 moles of chlorine. So we're going to have to times that bad boy by 2. Look how slow I am. Honestly, when you get older, you don't get thicker, you get slower, your reaction times and stuff. But that's what I'm saying anyway. Apparently you don't get a bit thicker till you're about 80. You actually retain your intelligence. I was reading, which I was finding really good. You kind of retain your... At my age, you don't really get any more smart. You just retain your intelligence, but you get a bit slower on everything. So what the hell is that? That is the atomization of strontium. Okay, which is +164. Hey, you guys are all over it. Invalido, very close. I think you're 3 out somehow. I think you should get -730. And then divide by 2, because what you've worked out is the electron affinity for the 2Cl gaseous to 2Cl minus. You've worked it out for 2 moles. Okay. You need to divide by 2 to get the electron affinity for 1 mole. So it's going to be -365. So well done. So you can do that in either method. So if you want to do, hopefully, have I already done this? I might have done. Yeah. Is that -2112? Yeah, that is. Oh my gosh. Yeah. Yeah, so the correct answer, you should get -730 and then divide by 2, -365. Yeah, it's horrific. My writing on here is horrific. So you can do either method. I would type it all out again and show you, but that's just long, isn't it? If you want to do the other method and you're like, I hate these arrows, just write -828 equals +164 +121 times 2. So you could write plus 242 if you wanted, plus 121 times 2, plus 548, plus 1060, plus x, plus minus 2112. Add all the numbers together, so you've got minus 828 equals something plus x, and then subtract whatever that is from both sides to get your final answer. Yeah, I need that drawing pad. Yeah. Look, check out my laptop. Things are breaking, man. Things are bread and look, check out the laptop screen. Yeah, that's like it fell. I dropped my laptop, so I need a new laptop as well, which I am gonna get. Actually, I've already got one, but I haven't. Oh my gosh, is that even that? I mean, yeah, I don't even know if that is looking at me or looking at my forehead. Anyway, light blasting off my forehead. I should have my cap, but I've washed all my caps and they've all gone bent and out of shape. The reason I wear caps indoors when doing the lives is because otherwise the light luminesces off my bald head. It's my secret power. Right, now, do we want to do any more of these? Probably no. So, yeah, I had a big giant, like a couple of years back, I had a massive giant all-in-one touchscreen. I wouldn't go all-in-one again. Once they sort of break down, the screen is still perfect, but the rest of it doesn't work. But the touchscreen was really good for drawing and writing. But yeah, I'm going to sort it out. My wife uses a drawing pad when she's teaching in school, like, or she uses something like that, one of them touch pads. But there's so many new things coming out all the time. I probably need to have a look and sort it out. Right, I've got more lattice enthalpy questions. But let's move on to something else. I've got loads more lattice enthalpy questions here, but I want to move on to another concept before we finish up. So this is the enthalpy of solution. So yeah, what is all this about? I probably should get, let's go to a blank screen first. Okay, so yeah. Ionic compounds, ions, we can think of them as perfect spheres, like a football, positive ion and a negative ion. However, there's no ionic compounds that are purely ionic, because what happens is the positive ion pulls the outer electron from the negative ion, pulls the outer electrons towards it, and we know a covalent bond is when they get shared. You get like a partial covalent bond or partial covalent character. So this affects, and this is what you're seeing here, this small positive ion is distorting the anion, the negative ion, and pulling the negative outer electrons towards it and distorting the electron cloud, so that at any 1 second the probability of the electron being around the negative ion, well, it's been stretched a bit. And this gives it partial covalent bonding, which is a term you can use in your exam. Now, how does this affect? This affects the lattice enthalpy of formation. Essentially, it affects the strength of the lattice. So when we do the theory, when we do the Born-Haber cycle, and we do the theory on the Born-Haber cycle, so when you carry out the Born-Haber calculation, like we just did with the old Born-Haber thing, what we get is, we get, like, say for magnesium chloride, if you worked out the lattice enthalpy of formation, it's minus 2326. However, in real life, when we do the experiment, we're like, oh, it's actually minus 2526. What's going on there? It's not the same. And so there's something happening there. And look, when magnesium bromide, when we actually carry out the experiment with magnesium bromide, it's even more exothermic, suggesting it's even more stable than we think it's going to be. What's going on? It's called polarization. So what's actually happening is, where you have a discrepancy, means funky word that, where you have a difference between the experimental value, the real value, and the theoretical calculated value, it means the less and less, well, it basically tells you that your ionic bonding is not purely ionic, and that you have some covalent character. So you look at which one has the biggest difference and you say that one has more covalent character. There has been polarization has occurred and we've got partial covalent character. So when we look at this, we see magnesium chloride and we look at the difference and we go, look, there's a 200 difference. But when you look at the magnesium iodide, it's bigger than 200. It's nearly 400 difference. So that's right. Yeah, that's right. It assumes that there's no covalent character, the theory. But actually, if we check out magnesium iodide compared to chloride, there's a reason why it's more distorted, the magnesium iodide, and it has some covalent bonding with the ionic bonding. So covalent character in important 45 means, you know, in covalent, so look, here is ionic, right? And this ion could be a chloride ion. Its little electron is buzzing around there. That's a perfect. Oh my gosh, what the hell is that? This would be covalent, where they're like that. And in between, we have, like, this is the most crustiest drawing ever. But in between, we have this, where the outer electron is being pulled towards the positive ion, the metal ion, so that it's distorting and almost becoming like it's almost popping over into the outer shell of the metal ion, if you think of it like that. It's being distorted, the electron cloud. Remember, this is just the probability of where the electrons are. You can't distort the positive ion. You can't move protons. The most stable subatomic particle in the universe is a proton, right? Protons are really, really stable. It's why we use the number of protons as the atomic number. It doesn't change normally for an atom. That's why it's the atom's number. But you can easily change the electrons. So electrons can get distorted, they move, and they can get pulled there. And when you get that, we call it partial covalent bonding or covalent character. So where do we get the biggest kind of, where does this happen? Where do we get the biggest impact of this polarization? We get the biggest if you have small positive, big negative. When you have this situation, you're going to get like massive, okay, that looks like a dog that's fallen asleep. But you're going to get big polarization. Whereas if you have big positive, big kind of same size negative, you're not going to get a lot of polarization, right? And so how do we describe that? So you want small positive ions have a high charge density. So this is the key terms you need for this topic. You just need to say small positive ions have high charge density. Now you are looking at the charge as well, like a 2+ ion of the same size as a 1- ion. The 2+ ion will have double the charge density. So you've got to look at the atomic radius as well, take into account what happens going across the period, that kind of thing. So you get the idea, right? Small positive ions, high charge density, and then they're going to be more polarizing. And then large negative ions. Large anions, just another name for saying negative ions. So large anions are more easily polarized. Why are large anions more easily polarized? Because the outer electrons are further away from their nucleus. They're held, there's less of an electrostatic attraction holding them in, so they're more easily distorted and pulled towards the positive ion. Okay. It's a little bit like the Pauling scale, yeah, there's a little bit, but yeah, yeah, I don't want to confuse you, but yeah, electron affinity is weird as well, but yeah, electron affinity and electronegativity are two different things, so yeah, but never mind, right, let's move on. Okay, so bearing in mind that if you're small and positive, you're very good at distorting negative ions. And if you're a big negative ion, you're easily distorted. Let's have a look. Which of the following is the most covalent? Now, these are all ionic, so we don't want to turn around and say it is covalent. We want to say has the most covalent character, or has partial covalent bonding, or as they like to put it, the most covalent character. So in which one has the anion been polarized the most? No, Gala, that is a really good point. They're both important, and you'll get situations like this where you're going to go, okay, so you've got to think it out in your head. Magnesium. So you're going to go Mg, same size. So I don't know why I'm writing Mg. I could just write 2 plus, right? What stupid idiot. Right. Oh, God, that's just ugly. Right, let's get rid of all of that. What are you saying, people? You already got your answers up? Right. Nice. So, +2, +2. These are the same size. So I'm going to cancel out A and B first. Let's work out. F minus 10 electrons. Smaller than bromine. I can't even remember what bromine is. What's bromine? It's like 80 or something stupid electrons. So bromine is bigger. Why have I bothered putting the elemental symbol? I should have just put a minus. See what happens? So, and what does this mean? This means that this is going to be distorted more. This one, now it looks like a duck. I've drawn a duck. Okay, this one is more distorted. Let's get rid of that. That is not as covalent as this one. So large negative ions, the electrons are further away. Now here's where you might get confused with electronegativity. You might turn around and say, but sir, fluorine's the most electronegative. Absolutely. Fluorine is pulling its electrons towards itself. The nucleus is very close to the outer electrons. Fluorine's like, you ain't taking my electron, fool. And it's keeping its electron in close. Whereas bromine is a larger anion. The electron's further away. It's less easily pulled in. So actually being less electronegative is going to make you polarized more easily a little bit. Potentially. So I'm going with, at the moment it's looking like B, but now we've got to check out these two bad boys. And we have to say aluminium is +3. You guys are right. And aluminium is 1 across from magnesium. Don't the atomic radii get smaller as we go across the period? So yeah, I definitely think it's going to be one of the aluminium ones. And then we're going to do the same thing. The fluorine is not going to be as easily polarized as the bromine. So it's going to be D. So well done if you put D. Yeah, it's going to be D. This is my drawing of D. So yeah, well done if you put D. You are definitely on track. Cool. Right, let's do another one of these. Oh my good gosh. Table 2 shows the theoretical lattice enthalpy based on a perfect ionic model. Perfect ionic model is your theoretical. That's where we imagine they are perfect spheres, point spheres or whatever they call them. And an experimental. So there's a difference. Why is there a difference? 1 mark. Yeah, D was the answer when we did the... Was it the biology lesson or was it my last chemistry lesson? I can't remember, but it was D every time. Okay, so covalent characteristics. You've got to be careful with the word polarization. I'd say the anion as... What is it? Silver chloride. Right, let's be careful with the word polarization because you might get that mixed up with polar bonds and start talking about polar bonds and stuff, right? Like you remember dipoles and intermolecular forces, you might get yourself all in a tiz. What we want to do is who is being polarized? So who's being polarized? Well, it's going to be the chlorine, the chloride that is polarized. The one that gets out, the silver's not polarized. The chloride has been polarized. So we probably want to, we might say the chloride ion has been polarized or distorted. So it's no longer a sphere, it's been distorted, or we can say it has covalent character. All of them should be good. Let's have a little look. Oh my gosh, what happened there? Okay, let's have a look at the... I've got the exam board answer here somewhere. Where is it? Oh, there it is. And they're a little bit naughty here. They don't accept something that you might be upset about. Chloride ion has been polarized. Chloride ion distorted. Ignore it is not a perfect... Ignore the ions are not spheres. So they don't want you to say the ions are not spheres. And that's a bit mean. If you'd said the... And the reason is I think they want you to say the chloride ion is not a sphere. So I think that's why they're like... So it's better to say the chloride ion has been distorted. Do not allow references to molecules or ions with covalent character. Do not allow it. It is covalently bonded alone. So you can say it has covalent character or partial covalent bonding. They don't want you to say molecule because this is not a molecule. Okay? So what they're saying there is it's not a molecule. And this is tight, man. This is language tight. Ions have covalent character. They don't want you to say the ion has covalent character. They want to say the silver chloride has covalent character. So like, it's very stingy that. But you could just say it has covalent character or partial covalent bonding. But that is nasty. It's a language thing. Yeah, it's a language thing. It's a language thing. If you say the ions are not spheres, they could say to you, well, the silver ion is still a sphere. It's the chloride ion that's been distorted. So you're saying both ions have been distorted. So they can get like that. And then if you say it's a molecule, they'll be, well, it can't be a molecule because you don't get ionic molecules. It's an ionic compound. It can't be called a molecule. A molecule is like a chlorine molecule or an oxygen molecule, small covalent molecules, right? So they're being really languagey there, which is annoying. Yeah, that is mean. All right, let's do one more of these. Lattice enthalpy values can be obtained from Born-Haber cycles and by calculations based on the perfect ionic model. Which compound shows the greatest percentage difference between these two values? What, this particular question? One of my lattice enthalpy questions was OCR that I did earlier, the Born-Habers. This, I believe this, looking just from the style of the writing and the font, this looks like an AQA question. Gertie, this one is an AQA question. But you definitely do Born-Haber cycles in OCR. Okay, D is lithium iodide. I think you guys are right. Lithium and cesium are both +1. So +1, +1, +1. Lithium is smaller, higher charge density, and iodide is the larger negative ion. So you're looking for small positive, large negative, boom. And also check the charges. Those are they're all +1 and all -1. So yes, the answer is D. So well done for getting that right, guys. You guys are amazing. Yeah, that's some weird dude dancing. Okay, yeah, enough of that, but yeah. Right. What is this? I'm dying. Right, couple more questions, then I'm done. So, what have we got? Table 3 shows the enthalpy of hydration values for ions of some group 1 elements. Okay, quick reminder, I did this right at the start. No, I didn't. Oh. Enthalpy of hydration. I didn't talk about that. I talked about the enthalpy. I talked about the enthalpy of hydration. No, I don't think I did. Enthalpy of hydration is like, it would have helped if I'd done some enthalpy of hydration. I didn't actually tell you anything about that, so maybe I should just skip that. But enthalpy of hydration is essentially, you've got your gaseous, like lithium, I don't know, gaseous lithium chloride ions, whatever. Let me just bush this out, right? You've got your lithium chloride, and then what you're going to do what happens, you take these bad boys and you make them aqueous. And the lithium is going to form interactions. And the chloride ion is going to form interactions with water molecules. So when we make them aqueous, you're going to form some interactions between the delta positive hydrogen, the negative chloride, or the delta whatever. This is just about lithium, so let's get rid of the chloride because these are about just metal ions. So it's just going to be a attraction between the lithium positive ion and the delta negative oxygen. And obviously, the enthalpy of hydration for lithium is exothermic. So what does that tell us about the attraction between the lithium and the delta negative oxygen? Yes, no. Would it always be exothermic? If it wants to be dissolved, it will. Yeah. If it loves being aqueous, if the ion is forms strong interactions with water, then it will be. So the stronger this attraction, the more exothermic, because the more energetically stable it is, the more energy it will release. And I guess we're going to do the charge density, right? We're going to go charge density. So if we go potassium is bigger, therefore that positive charge is spread out. It's not as sexy time for the oxygen. So yeah, this is a weaker attractive force. So the potassium will not lose as much energy. It won't go to as low energy level, so it's not as stable in its aqueous form as lithium is. Okay, yeah, it's a weaker attraction. So that's basic. So what we want to say, explain the enthalpy of hydration becomes less exothermic. So we want to say the potassium ion has a larger charge, smaller charge density. So we want to say, oh, potassium ion's got a smaller charge density, lower charge density. Therefore, it has a weaker attraction to the delta negative oxygen on the water. So that's what I would put as my answer, but I'm not going to type. If I start typing, my screen will start moving, maybe if I click on the thing, so maybe not. But the perfect answer to this would be, you can see the potassium's bigger, so you'd say potassium ion is bigger. You don't need to say that. You can just say the potassium has a lower charge density. So the charge is spread out over a bigger ion. So a lower charge density. Therefore, it has a weaker attraction to the O delta minus than the lithium ion does. There you go. Okay. One more thing. I probably need to... Yeah, so this is slightly different. We've just looked at gaseous ions, and these ions here are gaseous. Look, they got a G next to them. This is ions in their gaseous state going to aqueous. Guess what? We can go another route. We can go just straight from the solid ions in the lattice. We can just put them into hydrated ions like that, and this is the lattice enthalpy of solution. So this is called the lattice enthalpy of solution. I know my face is over the word solution, is it? Yeah, my face is over half the word solution. But so we can go from just take some salt, stir it in some water, right? And most of these are going to be exothermic, but it depends on the attraction between the delta negative oxygen and the positive ion, and then if it's sodium chloride, between the chloride ion and the hydrogen. The stronger those attractions are, yeah, the better it, I guess the better it's going to sort of dissolve. Now, what do we want to do? We want to do a question. What is that? Yeah, kind of like hydrogen bonding. It's really just, it's best to stay away from saying hydrogen bonding. I'm just going to call it the attraction between the, because hydrogen bonding, you always think of O's and H's and stuff. So, but yeah, I would just talk about attractive forces. But yeah, so all this is saying, right? So now this is enthalpy of solution. The questions are always cycles like this. And it's just really showing you that the enthalpy of solution is the energy change. So delta H, when you take solid salt, sodium chloride, and you dissolve it into sodium ions and chloride ions, AQ. But you can go an alternative route. And we can dissociate it first. That's your lattice dissociation enthalpy. Do you remember we could work that out from a Born-Haber cycle, the lattice dissociation enthalpy, by working out the lattice formation enthalpy and then reversing the sign. So you can go that way instead, down to the, and which basically goes from a solid lattice into gaseous ions, and then you can hydrate the ions. So it's just, they're just going to give you 2 out of the 3 and you work out the third. That's all they're going to do. So let me give you an example. There we go. We're going to finish in about 10 minutes. So see if you guys, this is a CGP one. So any of you got the old CGP, you can have a sneaky look if you, but you could just try and work it out on your calculator. It's not hard. So it's just saying, what is this? The enthalpy change of solution. And they're giving us the numbers. The lattice dissociation enthalpy would be positive. You're breaking a nice stable salt crystal lattice into gaseous ions. So you're going to put a lot of energy in to do that. And then we're hydrating these gaseous ions. They're like, yeah, get me in solution. I'll be more stable. So that's going to be exothermic. So minus 506 for the fluoride ion. And the enthalpy of hydration of strontium 2 plus is minus 1480. Who can come up with the answer? Yes, because Inbalido and Gertie have a, what have you got to do with that? How many fluoride ions are there? So you've got to check your moles. So check your moles. So because we've got 2 fluoride ions, we need to do 2 times minus 506. So we want to do 2492 minus 506 minus 480. Cool. 0. And by the way, I don't think it's in your specification, but they call substances like strontium fluoride here, they call these ideal solutions if they have a 0 enthalpy change. They call this an ideal solution, but I don't think you have to know. You don't have to know that. It's not in your spec. But if you're doing a chemistry degree, you'll come across that, ideal solutions. And the idea is that, why is it an ideal solution? It means the bonds between it and the solvent, in this case we call it water, the bonds between the water and the strontium fluoride are equal in strength. The overall change is equal, basically. So it likes being dissolved in the water just as much as the water likes being. So the water is attracted to the strontium and the fluoride as much as it is attracted to another water molecule. So there's no overall energy change. And they like to use these to calibrate equipment and as standards, but you won't need to do that unless you do a degree in chemistry. Yeah, ideal solution. You won't need to do that, I don't think, unless you do a degree in chemistry. Right, last question, and then I'm wrapping up for the day. So, or for the evening. Right, magnesium chloride dissolves in water. Given equation including state symbols to represent the process that occurs when the enthalpy of solution of magnesium chloride is measured. So you've got to write an equation out for when magnesium chloride is basically put in a solution. So that's dead easy. Nothing funky there. It's not the hydration. See, it's chemistry. You've got enthalpy of solution. Hydration's from the gaseous ions. Solution is just from the lattice. So enthalpy of solution equation is just from the lattice. So we're just going to do a few more 5 minutes and then I'm done. Now I've got a biology lesson going on Thursday at 7 p.m. for those of you that do bio, and I can't remember what's... Oh, there's a poll up at the moment with aerobic respiration, anaerobic respiration, cell membranes and transport, and something else, and I can't remember what the fourth thing is. At the moment, the leading candidates for what I'm going to cover in the lesson, I've kind of been a bit naughty because I separated aerobic and anaerobic respiration, and they equal 45% of the votes, and cell membranes are in the lead. They also equal 45, but I separated aerobic and anaerobic because I thought it'd be too much to go through in one lesson, all the Krebs cycle, all the stages of aerobic and then the anaerobic. So I will cover, if they don't win the poll, I will cover them at some other point, because that was quite popular. But at the moment, it's cell membranes and transport people want to go through. So the mechanisms of things moving across the cell membrane, talking about how glucose is absorbed in the gut by co-transport, facilitated diffusion, or indirect active transport, or whatever, all of that business. So transport across the membranes and the structure of cell membranes. So that's in the lead at the moment. Yeah, water and inorganic ions was on there. That's the fourth one, but that's in last place at the moment. Hydrophilic and hydrophobic, like in bio. Yeah, I think maybe. Yeah, I'm trying to think where. Yeah. What hydrophilic is when you're yeah, yeah, I'm trying to think. I can't think off the top of my head in A-level chemistry where you use it, but it is a term meaning water loving and water hating. So you're basically you're not going to form hydrogen bonds or interactions with water, or you are going to form interactions with water. Yeah. Part D to this. Have I skipped something out? I don't even know what question this is. Give an equation including state symbols to represent the process that occurs when the enthalpy of solution of magnesium chloride is measured. So what you should do here is just MgCl2. That's going to be solid. And then we're going to go to, oh my days. O 2 plus AQ. We're going to be in our ions. And that AQ means they're surrounded by water molecules. And then chloride ions. And I need 2 of them and AQ. And that would get you to 1 mark. Cheers. Thank you. Thank you. Thank you. Part D. Is that to... Is this A? This may have been linked to a previous question. I'm not sure. I just ripped out part of this. So, table 2 shows... Oh! Use your answer to part D. Yes. Yes. This must be part D. This must be part D. Why are they saying use your answer? Because you need the ratio, the numbers in that balanced equation. That must be part D. Thank you for that. I was wondering what that was on about. So what we're going to do here, we're going to write this enthalpy of solution out. Oh my gosh, have I got to write it out again? I've got to write it out again. Excuse my handwriting, people. This dirty mouse pad has got to go on the laptop. But yeah. So, okay, this is the enthalpy of solution. We want to find out this. Oh gosh, symbols. Oh my good gosh. Why have I put double plus, not the double plus? And then plus 2Cl minus. Oh my days. You can draw a little Hess's law thing. This is some messed up stuff. Right, so enthalpy of lattice of dissociation of magnesium. So if I want to dissociate the lattice, that arrow must go down, right? I'm going to break that. What do you break it into? You break it into its ions in their gaseous state. So 2 plus gas plus, you don't, by the way, you don't actually have to write all this out. Some people like to visualize it, but so that would be lattice dissociation enthalpy. And then the enthalpy of hydration is basically going from the gas to the aqueous. You could just do 1 arrow. I'm going to put 2 arrows just for the sake of it. You wouldn't normally put 2, but just showing that we're going from that, to that. So we just need to write the numbers in. What is that? Plus 2493. And of course, we're going to follow this round anti-clockwise, like we always do in these cycles. And where the arrows line up, and they always line up in this one, we just keep them the same, right? So enthalpy of hydration, what is that? Of magnesium is minus 1920. That is, chlorine is minus 364. Need to times that by 2. What'd you get, guys? Minus 155. That sounds pretty good. And does that make sense? Should it be negative or positive? It's the enthalpy of solution. It's exothermic. Yeah, yeah, we'll go with that. It's not super exothermic, but yeah, that's the right answer. So yes, 2 marks. Nice. Yeah. Then it says the enthalpy of calcium 2 plus ions is minus... No, the hydration. So they switch up now in part, whatever this is, F. This might be part F. They switch up now and say, they start talking about hydration. So the enthalpy of hydration of calcium ions. Oh, right, because we've got the hydration of magnesium over here is minus 1920. Okay, I'm with you. They're basically saying, why is it less exothermic than magnesium? What's the answer, peeps? I'll put the I'll put a poll up of things. No problem, Brass Boy. I'm about to finish. Right, calcium. Is it the bigger ion or smaller ion? Yeah, you're right. Calcium's the bigger ion. So what does that mean? Thank you. Thank you. Yeah, that's a really good answer. Lower charge density. Ca2 plus has a higher atomic radius, but same charge magnitude, so it has a lower charge density. Yeah, less charge density. Well done, well done. Listen, Olu, if I have to, I'm going to butcher your name if I try to say the whole thing. So for the shout outs, you came out with the lower charge density first, so well done. But yeah, I'd have to practice that off camera before I say that and then myself. I know. Right, guys, I think that is going to be it. I think we're going to finish there. So we covered Born-Haber cycles today. We looked a little bit at hydration and enthalpy of solution, and you're going to do that in A2 if you haven't started yet, so you'll have a head start. And if you're in A2, it's revision. If you understood all of that and you can practice that, loads of these questions on physics and maths tutor. If you're AQA, you will do you can practice the OCR if you've done all the Born-Haber. Now they split on PMT, physics and maths tutor, they split the Born-Haber into, they split all their question packs into the exams up to like 2021, and then they go like 2022 to 2024. They have a new pack. So be aware there's 2 packs for each set of questions. So if you're doing thermodynamics, they have like 2 sets of questions. You might want to work through both sets. But once you've exhausted all of that, you're like, oh my God, I need more exam pressure questions. You can go for the OCR ones. They will have a slightly different style, but they're going to do, they cover Born-Haber as well. So yeah. Okay, guys. Good. Yep. So we're going to finish. So nice one. Thanks for showing up, guys. And I will catch you next time.
I've had training.
The training is nothing. The will is everything.
The will to act.
Yield.
You're still here?